Okay, so today we're going to be talking about geometric proofs. So a proof is basically justifying one of these theorems we've been telling you about. So we've talked about medians, and we've talked about mid-segments, and we've talked about corresponding angles and supplementary angles and alternate interior angles, all that different stuff. So we've thrown a bunch of theorems at you the last week or so, 2 weeks, I guess. Now we're going to actually prove those theorems. Like, why do these theorems work and stuff like that. And we need to justify each step as we go through this process. So, first of all, I'm not going to do a ton of videos on this because once you do a couple of proofs, they're all pretty much the same. It's just basically using different properties to justify until you get to a point where you can prove one of your theorems, basically. Okay? So, first things first, let's start by talking about some of the theorems we're going to be using today. So, vertical angles mean those are angles, I guess I'll do an example here of each one. So these are angles that are opposite each other at an intersection. So something like that. So we see an intersection, those are vertical angles, and it just means they are equal to each other, right? A corresponding angle is if I have two parallel lines. So two parallel lines, and I have a transversal. A corresponding angle would be an angle, or a pair of angles, that are in the same place in each intersection. So like both of those are in the top left. Okay? Alternate interior angles, same idea with parallel lines with a transversal. Those are inside the parallel lines on opposite sides, on opposite intersections of the intersection there. Let me zoom in a little bit so you can see what I'm doing. Okay, so that's an alternate interior angle, right? Other side, other intersection of each transversal. And then a perpendicular bisector theorem. You guys haven't necessarily heard this one before, but I mean, you should know what a perpendicular line is, right? So if I have a line segment, and I have a line that intersects it perpendicularly, so like that, that means it's intersecting at 90 degrees, right? Basically what the perpendicular line, or the perpendicular bisector theorem says that no matter where I am on this line, I can draw lines from any point there and they would be equidistant from that point to the segments of the bisecting line. Okay? So that's all it's saying, and we'll actually prove that one in a second, or use it as a proof. But let's start with this one right here. So it wants me to prove, or do a proof of corresponding angles. And it's going to give me that lines Q and R are parallel. So basically that those lines are parallel. And the angle 1 and 5 are corresponding angles. And it wants me to prove 1 and 5 are equal to each other, or congruent. We're going to be using the congruent symbol a lot, which is just an extra little curvy line, right? So I know that these lines are equal to each other. I know that 1 and 5 are corresponding angles. So they aren't numbered here. So generally when you number or label anything, if we're labeling angles, we start in the top left and we go in clockwise order to label our angles. Okay? And since we have two pairs of angles, that is how you would label it. So basically it wants me to prove that this angle is equal to this angle. Okay? Now, in order to do a proof, we need to start off, and let me adjust my camera here. Okay? We always start off with basically two columns. We have a column where we state So our statements, and those are basically facts or something that we know. And then the other column is going to be the reason why we know it. So that's our reasons, okay? And that's basically how you start off by doing a proof. So the first things first, I'm going to start off by listing the things that are given. It tells me that Q, line Q is equal to, or not equal to, parallel to line R, and the angle 1 and angle 5 are corresponding angles. So there's my first statement, and the reasons I know that is it was given to me. Okay, so that is my given knowledge. Okay, so I want to now prove that 1 and 5 are in fact equal to each other. So to do that, I'm going to use some other things that I know about angles. First thing I'm going to use, now probably the easiest way to do this is to use the supplementary angle idea. So supplementary angles mean that anything that forms a straight line add up to 180, right? So right here I know that angle 1 and 4 are supplementary, right? They form a straight line. So I'm going to list that down. Angle 1 and angle 4 are supplementary. Okay. And I know that because angle 1 and 4 form a straight line. Okay. Now looking over here, I also know that angle 5 and 8 are supplementary, right? So that means that angle, or sorry, I don't want to do 5 and 8, I want to do 5 and 4. These are supplementary because again, they form a straight line. If I look at those and I take angle 4 and I put it where angle 8 was, it would be a straight line, right? Those two angles, and plus that's consecutive interior angle theorem, which I can use. I can use either of those. So I either know 4 and 5 form a straight line using supplementary, or I could use the consecutive interior angle theorem that says that they form a straight line as well. So one of those two, I'm just going to call it supplementary. So 4 and angle 5 are supplementary. Because really that's all that the consecutive interior angle theorem says, is that they're supplementary. So it's just taking out an extra step there in my reasons. So angle 4 and 5 form a straight line. Or straight, I should probably say straight angle. Same with that one, angle. Okay, then let's go through and describe what supplementary is. So angle 1 plus angle 4 equals 180. Angle 4 plus angle 5 equals 180. And I know that from the definition of supplementary angles. Okay. Then, with that information, it should be pretty easy to prove now. I should be able to say, well, angle 1 is equal to angle 4, or sorry, I'm phrasing that backwards. 180 minus angle 4. right? In the same way, I can say angle 5 is equal to 180 minus angle 4. Hey, I'm taking away the same measurement here, right? And again, I could prove that with, that'd be the subtraction property of equality right there. Subtraction property of equality. Okay? And then that would tell me that angle 1 does in fact equal angle 5, because they'd be the exact same thing, because if I took them out, it doesn't matter, they're equal to the same thing right here, right? And we call that the substitution property. If you remember back from 9th grade or from secondary 1. And that is a proof. Okay? Seems a little bit drawn out, but again, you'll have like a list of theorems and stuff you'll need. You just basically are plugging them in where you think you could prove something. Okay, let's try another one. That one was a little bit more complex than I thought it would be. Let's try this one. Let's try the perpendicular bisector theorem. So this one wants me to prove the perpendicular bisector theorem given CD is perpendicular bisector of AB. Okay, so this one actually has the diagram all labeled. So AB is my line segment, CD is the bisector, and it's perpendicular. So that means that it's intersecting at exactly 90 degrees, and it's bisecting AB, which means it's cutting it in half, right? So let's set up our statements. And I'm trying to prove that AB is congruent to BC. Wait. That is a typo. That should be AC. AC. Sorry. Okay. Statement. And reasons. Here we go. We start off by going with what is given to us. So I know that the line segment CD is a perpendicular bisector of AB, because that is given. Okay. So looking at this, probably the easiest way to prove this, because you'll notice I'm trying to prove this line is equal to this line, right? If I can prove these are congruent triangles, that means all the sides would have to be the same, right? So that's probably the process I'm going to go. I'm going to try to prove congruent triangles. And remember, there's 4 theorems. There's side, 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 angle, side, and I think that's what I'm going to go or try to prove, because that looks like the easiest thing to prove here. But there's also angle, angle, side, and what is a side, angle, side, angle. Okay, those are the 4 theorems. But let's try and prove side, angle, side. So first of all, an easy one. If this is in fact a bisector as is given to me, that means that this line has to be the same as this, because it is bisected. It's cut exactly in half, right? So right off the bat, I can say AE is congruent to line BE. Okay? Because of the definition of bisection, or a bisector. Definition of bisector. Okay. Then I can also prove, since this is a perpendicular bisector, that this angle is 90 degrees and this angle would be 90 degrees, right? That's the definitions of a perpendicular line, right? That it intersects at 90 degrees. That means that those angles would also be equal to each other because they'd both be equal to 90 degrees. So angle CEA would have to be congruent to angle CEB, and they're both equal to 90 degrees because of the definition of perpendicular. Okay. And then looking at my shape again, so I've proved these sides are congruent, I've proved these angles are congruent. Side, angle, side, I need another side, and it needs to be in order, right? So I need to prove that this side is congruent. Well, that one's an easy one, right? Because CE is a shared side. So CE has to equal CE. Okay, CE has to be congruent to CE because of the reflexive property, which says everything is equal to itself. So reflexive property. Okay. Now I have just proved side, angle, side. Side, angle, side. Okay, so that means that triangle CEA is congruent to triangle CEB because of side, angle, side. Okay? Which that also tells me that line AC is congruent to line BC because of congruent triangles, which means all the sides have to be the same. Okay, so I'll zoom out here a little bit. You guys can see my proof in its entirety. There it is. So started with what was given, figured out the two lines were congruent because of the bisector, figured out the two angles were congruent because of the perpendicular aspect of the bisector, figured out that the shared side was the same because of the reflexive property, and then with that information I could tell that these two triangles were congruent, which means that the last two sides there would also have to be congruent. So I just proved basically the perpendicular bisector theorem, which again says that like any point on this bisected line is equidistant to the line segment on the bisector, right? So that means that these endpoints would have to be exactly the same. Okay, and that is a geometric proof.